Alright, so we are going to look at an example problem for percentage yield. So as we know, chemical reactions don't always happen perfectly ideally. It's very possible and is usually the case that you don't actually produce as much product as you think you're going to for so many possible reasons. We can actually quantify that with a percentage. So in this question, we are told that Omar is working as an organic chemist and he reacts 10 grams of CH4 with excess chlorine gas. He obtains 10 grams of CH3Cl and some hydrogen gas. And we want to know what is his theoretical yield of CH3Cl and what is his percentage yield. So our first step here for part A, our first step is actually going to look pretty similar to a stoichiometry problem. Because to determine the theoretical yield, that's really what stoichiometry is. It's theoretically how much could be made. So we know from the first sentence of the question that Omar is working with a mass of CH4, so we know that the mass of CH4 is 10 grams. And the theoretical yield of CH3Cl, that's going to be a mass of CH3Cl. That's unknown. So we're given a mass, and our theoretical yield is also going to be in a mass. So that makes this a mass-to-mass stoichiometry problem. So it's really important that we practice our stoich because it carries through. So our next step, we've identified given an unknown and we've determined the type of problem that it is with regard to stoichiometry. So we now need to make a balanced equation. So we can extract that information right from the question. We know that CH4 or methane is going to react with some excess chlorine gas. That just means we're not going to treat it as limiting reactants. That'll be a different lesson. And we see that Omar obtains CH3Cl and some hydrogen gas. Right, we know that the chlorine and the hydrogen, they're both diatomic, Hofbrinkel. So now we need to balance this equation, which I'm just going to do quickly since we've had lots of practice already with balancing. So we found the molar ratio. To react completely, you have to take 2 moles of methane for every 1 mole of chlorine to produce 2 moles of CH3Cl and 1 mole of hydrogen gas. So now this just becomes a stoichiometry problem. So again, with mass to mass, we can't convert directly from mass to mass. We have to find moles. So the moles of the methane, or the CH4, we know that Omar took 10 grams. And the molar mass of CH4 is around 16.0426 grams per mole. And we know that we set up that equation properly because the units of grams will cancel out. This is going to give us approximately 0.6233 moles of CH4. So now we have found the moles of the methane that go into the reaction, and from there we can start to determine the moles of the CH3Cl that we're going to form. So with that, we can just set up another equivalent proportion multiplier like we've done in all the stoich examples. So we know that 2 moles of CH3Cl are produced per every 2 moles of CH4. And that's actually really nice because we see that the ratio there is 2 to 2, which means it's actually an equivalent ratio. So when we multiply that by the number of moles of CH4 that we have, again, we know that we've set it up correctly because the units of moles CH4 are going to cancel out to give us just the moles of CH3Cl. And since it's a 2-to-2 ratio, which means equivalent ratio, we know that we're going to form 0.6233 moles of CH3Cl. All right, so now that we know the moles of CH3Cl, we can determine the mass, which is going to be our theoretical yield, because that tells us theoretically if everything in this reaction happens perfectly, theoretically you're going to get this much of a product. It's actually important for chemists to know these kind of things because a lot of large-scale industrial processes rely on stoichiometry and trying to make reactions efficient so that you get a good percent yield. So we want to find the mass of CH3Cl. So that's going to be moles times molar mass, or 0.6233 moles times the molar mass there. I'm just pulling this directly from the periodic table. This is something that you would be expected to be able to do on your own. 50.4604 grams per mole is the molar mass. And I know that I've set up my equation properly because we're going to end up with final units of grams. The moles will cancel out. So when you multiply those two numbers together, you will get a final answer there of around 31.45 grams of CH3Cl. And then that is the mass. So for part A, we can then say, therefore, the theoretical yield is 31.45 grams of CH3Cl. All right, so now that we have that information, this here, we can move on to part B. So part B, just so we can remind ourselves, part B asked for what was Omar's percentage yield in this reaction. So we know that the percentage yield equation is percent yield equals actual yield divided by theoretical yield times 100%. And again, that just makes sense because all that a percent is a fraction out of 100. So in terms of actual yield, you might be thinking, well, how am I supposed to know the actual yield? Well, often, if you're performing an experiment, you're going to find the actual yield because you actually weigh out how much you've made. But in the question, he obtains 10 grams of CH3Cl and some hydrogen gas. So 10 grams, that was given to you right in the question. So in case anyone was confused about, hey, where do I get the actual yield? It's right in the question. So we know that 10 grams was the actual yield, but the theoretical yield, based on our stoichiometry calculations, was 31.45 grams times 100% to get a percentage, which gives us an answer of around 31.79%. So the percent yield is it's close to 32%, and that's not very high, but there are a lot of chemical reactions with much lower percent yields, and that we rely on for lots of things in industry. So the way that we would just finish that up would be, therefore, the percent yield is 31.79%. So just to recap, this started off like a regular old mass-to-mass stoichiometry problem. So those skills keep coming back, they don't go away. Started off as a regular stoichiometry problem in which we determine the theoretical yield. That's what stoichiometry does for us. And then the second part, more simply, we just compared the theoretical yield to the actual yield to determine the percent yield.